Basic operations. In this lesson, we cover basic operations of matrices including addition, scalar and matrix multiplication, and the transpose. Let's start with a general matrix with m rows and n columns. We say that A is an m by n matrix. A, ij, refers to the element in row I and column j of the matrix A. For example, consider the 2 by 3 matrix. The value of element A13, which lies in row 1 and column 3, is 7. The value of element A21, which lies in row 2 and column 1, is 3. The transpose of a matrix A, denoted by A superscript T, is formed by switching the rows and the columns of A. For example, the transpose of the matrix 1 4 7, 3 2 6 is 1 3, 4 2, 7 6. A matrix which is its own transpose is called a symmetric matrix. A symmetric matrix must be square. That is, the number of rows must equal the number of columns. Notice that a symmetric matrix is symmetric about its diagonal. To add two matrices, simply add their elements component-wise. 1 plus 1 is 2, 4 plus 3 is 7, 7 plus 1 is 8, 3 plus 5 is 8, 2 plus 7 is 9, 6 plus 3 is 9. Matrices can only be added if they have the same number of rows and columns. If we multiply a matrix by a scalar, we simply multiply each element of the matrix by that scalar. For example, 2 times the matrix 1 4 7, 3 2 6, is simply the matrix 2 8 14, 6 4 12. To multiply two matrices together, we take the dot product of the rows of the first matrix and the columns of the second matrix. That is, to compute the ij element of C equals AB, we sum the product of the elements in row I of A and column j of B. To compute the entire matrix C, we repeat this for every row of A and every column of B. For example, consider the product of a 2 by 3 matrix and a 3 by 4 matrix. The dot product of the first row of A, 1 4 7, and the first column of B, 2 1 0, gives us 6. The dot product of the first row of A and the second column of B is 11, and so forth. This gives us a 2 by 4 matrix. Two matrices A and B can be multiplied only if the number of columns of A equals the number of rows of B. When defined, the inner product of two matrices A and B is the transpose of A times B. The outer product is A times the transpose of B. Matrices are linear operators. And matrix multiplication is really just one matrix operator applied to another matrix operator. We can apply A to X. We can apply B to AX. We could continue by applying C to BAX, and so forth. It should be clear that BA does not necessarily have the same effect as AB. For example, suppose that operator A means put on your socks, and operator B means put on your shoes. Operator B applied to A would then mean put on your shoes over your socks. On the other hand, operator A applied to B would mean put on your socks over your shoes. Clearly AB does not equal BA. We say that A and B do not commute. Some operators can commute. It doesn't matter if you put on a hat before or after putting on socks. You get the same result. In other ways, matrices act just like scalars. Matrices are associative and distributive with respect to addition and multiplication. But, to distribute the transpose operator, we must first interchange the order of A and B. This is an important and useful identity. This identity can be shown by expanding the definitions in component notation. To convince yourself, it may be useful to multiply two matrices together as an example. Since the leftmost columns of U and V no longer contribute any information, we may eliminate them to construct an economy version SVD. This approximation gives us the best rank 1 matrix approximation to the original matrix. Let's examine a more interesting matrix. Suppose we take a 100 by 100 pixel image, as a matrix whose elements equal to the color intensities. Since there is structure to the picture, there is a lot of correlation between the columns. This means that the columns are close to being linearly dependent. Equivalently, the correlation matrix AA transpose is almost singular, which means that there are a lot of singular values close to 0. Here's a plot of the singular values of the matrix. The largest singular value is much larger than any of the others because of the bias in the data. The image is predominantly white. Let's examine the other singular values. The The large singular values contribute the most information about the matrix. Roughly half of the singular values contribute very little information. The rank of the matrix is more or less 50. Compare the singular values of the structured image of the sheep to singular values of a random matrix. The value of the elements of the random matrix were with the same mean and standard deviation as that of the sheep. Even the 100 singular value of the random matrix contributes significant information. On the other hand, we can project the image of sheep into a substantially lower dimensional subspace and still retain important qualitative features of the image. Let's take a look. I've only kept the largest singular value. The image is now a rank 1 matrix. This time we keep the largest 2 singular values. As more singular values are included, notice how the image of the sheep is rebuilt. Here's a rank 10 approximation. The image is clearly a sheep. Let's jump up to rank 20. And now let's look at rank 30. While there is change from rank 20 to rank 30, the change is rather minor. As you can see, a rank 100 matrix can be described by a much lower rank approximation.